So we've just finished talking about electrophilic aromatic substitution. In this video, we're going to learn about the opposite of that, which is nucleophilic aromatic substitution, sometimes referred to as SNAr. Now, you've seen two different nucleophilic substitution mechanisms in the first semester of organic chemistry. The first one that you learned about was the SN1 reaction. And just to remind you, these are going to be reactions where an electrophile, like an alkyl chloride, undergoes ionization as the rate determining step. And then this is then trapped by a nucleophile to give the product. Okay, so the step that determines the rate of the mechanism only involves one molecule. It's unimolecular, and that's why it's called SN1. In the other substitution mechanism you learned, SN2, what you have is the substitution of an alkyl chloride, for example, with a nucleophile, and it goes via this backside attack type of mechanism where the rate determining step is actually the nucleophilic substitution. So it involves two different species to get to the product, and so it's a bimolecular rate determining step, and that's why it's called SN2. Now for aromatic rings, neither of those mechanisms are going to be possible, at least with aryl chlorides. So for example, an SN1 mechanism isn't going to be viable because what you would have to do is to ionize to get to an aryl cation. So an sp2 hybridized cation is usually quite unstable, and so you are not going to see any dissociation of aromatic halide molecules, and so you'll just never be able to do that type of SN1 mechanism. By the same token, SN2 chemistry is not possible either. Remember, we're looking for backside attack to a sigma star orbital, and in the case of a benzene ring or other aromatic ring, the backside attack would actually be within the ring, so it's just geometrically not possible. So neither of those substitution mechanisms can happen with benzene derivatives. Okay, but then why does this reaction work? All right, so if we take parachloronitrobenzene and we treat it with sodium methoxide and methanol, we actually see that chloride substituted with a methoxy group. So how does that work? Well, let's look at just a couple more examples to get a few clues. So it turns out if we have orthochloronitrobenzene, that also works. It gives us the ortho product. If we were to have dinitrochlorobenzene and do the same reaction, we would also get the substitution product. The rate would actually be significantly faster than in either of these two cases. And then if we look at metachloronitrobenzene, same reaction conditions, and we don't see any reactivity. Okay, so orthopara seems to work fine, meta is unreactive. What's going on? What's happening? Okay. So what's happening is a special type of reaction of aromatics called the SNAr reaction. And so instead of SN1 or SN2, we have SNAr for aromatic. All right, so let's talk about the mechanism of one of these reactions. So we can just take the parachloronitrobenzene and we'll do this reaction with methoxide. Okay, so what's going to happen is the nucleophilic substitution, we have to have it occur at that site that we're substituting, right? So at the chloride site. And for the first resonance form, we'll just push the pair of electrons one position over. Okay, so that's going to give us the following resonance form. Right, so there's my methoxy, my chloride, and now I've got an anion at that position, NO2. And now a carbanion isn't necessarily all that stable typically. We wouldn't usually expect a base like methoxide to be able to generate a carbanion, whether by deprotonation or nucleophilic substitution. But in this case, it's not just any carbocation, it's actually one that can be resonance stabilized to a significant degree. So let's actually look at the resonance forms for this intermediate. And so what I can do is I can push that anion down, right? So this is an allylic anion, so I can also put my anion right there. Okay. And there is another resonance form that I can draw where I would put it up in the other sort of ortho position. Okay, so there it is. So those 3 resonance forms that we would sort of expect for the aromatic, but it's this one that's especially key because we put the anionic charge right next to the nitro group. And you might recall that the nitro group is a resonance withdrawing group. So we're able to draw resonance forms where we put electron density onto the nitro. So that's a very key resonance form for this SNAr mechanism. Okay, so what we can do here is to draw a further resonance form where we put the anionic charge actually now out onto the oxygens of the nitro group. Right? So we just push it onto the nitro group. And so that's a very good explanation for why the nitro group is such a great resonance stabilizer. It's because you're able to put that negative charge out onto the oxygens, which remember are very, very electronegative. So this is a very nicely stabilized anion intermediate, right, because of that stabilization. So there we've got our intermediate. That's the first step. And then the second step is, well, you know, keep in mind we've lost aromaticity, just like with electrophilic aromatic substitution where we formed a cation and lost aromaticity. We've done the same thing here in forming an anion. We want to get that aromatic stabilization back. So all we're going to do is just eliminate back out one of the groups, except instead of eliminating out methoxide, we're going to eliminate out the chloride. So I could do that from any of these resonance forms. It really doesn't matter. You might go ahead and see if you could do an arrow pushing mechanism from every single resonance form just to prove that you can get to the same product. But I'll go ahead and use this final one that we drew. So all I have to do is to push the electrons all the way back around and then ultimately eliminate out my chloride. And when I do that, I will have my SNAr substitution reaction. Okay, and it's just that easy. So really just 2 steps: add the nucleophile at the right position, stabilized anion, and then eliminate out the thing that you're substituting, right? So that's how that works. Okay. Now, how do we rationalize that these other isomers did not react, or how do we rationalize that the orthoisomer did react, but the meta-isomer did not react? Well, basically all you have to do is to evaluate the stability of those anionic intermediates, right? So anytime that we can get to an intermediate that does that, so if we compared this to the metachloronitrobenzene, so we'll do it like that, and right, so again, if we're going to substitute the chloride, that substitution has to start still at the position that the chloride's attached to, and we push the double bond over to the side. Okay, when we do that, we get to this intermediate, and we've still got an anion. Okay, but now that anion isn't stabilized, at least not by resonance, right? So we could draw different resonance forms around the ring, and I'll skip that for now, but if you do that, you'll see that there's partial negative charge there, partial negative charge there, and then of course where we've got it in this resonance form there. So those 3 carbons would feel that resonance, that anionic charge, but none of those are stabilized by resonance by the nitro group, and so it's just pretty much going to feel like an allylic anion, or an anion that's part of this 5 p orbital system. Okay, so there's nothing particularly great about that, and in this case methoxy isn't a strong enough nucleophile to make that happen. Okay, so that's why the meta reaction is not going to work. And incidentally, it's also the same reason why just a normal chlorobenzene is also not going to do SNAr type of chemistry. Okay, so your normal run-of-the-mill aromatics are such that they're nucleophilic. That electron cloud wants to be given up. They don't typically want to accept electrons. So you really do need a fairly strong electron withdrawing group to make that happen. So for that reason, SNAr reactions are not as common as electrophilic aromatic substitution reactions, but they do occur in a number of cases. Okay, so we could also then talk about some specific examples very quickly. So imagine that we had this molecule now. So this is very similar to what we just talked about, but imagine we treated this one with sodium methoxide and then in methanol as the solvent. What product would we expect to get out of this? Well, hopefully based on what we just discussed, you would realize that the parachloro substituent is prone to substitution by an SNAr mechanism, but the meta is not. So the product that we would get out of this is this chloromethoxynitrobenzene, okay? And this chloride is just going to stick around. It's not gonna move. So that's actually a pretty useful thing to think about or to keep in mind, that if you can put in two different halides and only one of them is going to be ortho or para to an electron withdrawing group, you can substitute one of them and get these somewhat more complex products. Okay, now the range of the nucleophiles, we can use a variety of things, and I think we'll probably work through some of that by the problem sets, but I'll just give you two last examples here of different things that you might think about. So one, we could treat this with a aqueous base, so something like sodium carbonate in water, and we're probably gonna have to heat this up, to be honest, to make it go. But if we do that, we can substitute the chloride with a nice hydroxyl group, okay, and then we'll get to this this phenol. So there's our nitro. Okay, so that's another way now that we know how to make phenols. It's not the most general because you have to have this substrate that's ready to do SNAr, but it could be useful in some cases. And then I will just show you one final one. We could actually take that exact same substrate and we could actually treat this with ammonia, NH3, and we're going to apply some heat. Okay, and if we do that, we could substitute that chloro for an amino group. Okay, so we'll get ourselves to an aniline product. Okay, and there are a variety of other things that that can serve as the nucleophile for these processes, but they all have to have some pretty strong electron withdrawing group that can stabilize those anionic intermediates. So that's the SNAr reaction.